everyone. The topic I'm going to share today is about introducing the M2L31 ReRAM controller. ReRAM, Resistance Random Access Memory, is a non-volatile memory that is regarded as a potential next-generation embedded memory and has broad application prospects in areas such as IoT devices, mobile devices, and embedded systems. By applying an external bias, the resistant state of the components can be changed to achieve the effect of storing digital signals. It has three major features: fast reading and writing speed, low energy consumption, and durability. Unlike embedded flash memory, ReRAM does not require erasure before writing, thus enabling faster writing speed. Its usage method is similar to EPROM, being simple and fast. Additionally, compared to flash memory, ReRAM consumes less energy because the energy required to store each bit of data is less than that required in flash memory. Moreover, since each storage unit can be independently set or reset, it is also more durable than flash memory. I will mainly share the following 15 parts: 1. Features. 2. Block diagram. 3. Memory organization. 4. Dual bank. 5. XOM. 6. OTP. 7. ReRAM memory map. 8. System memory map with IAP mode. 9. ISP 10. Embedded ReRAM memory programming. 11. CRC32 checksum calculation. 12. ReRAM all-one verification. 13. APROM function, safety protect. 14. Secure conceal function. 15. Lock effect tables. First, I will share the features. 1. Supports dual bank ReRAM macro for safe firmware upgrade. 2. Supports 4 execution-only memory regions, that is abbreviated as XOM, to conceal user program in APROM. 3. Supports 256 bytes user configuration block to control system initiation. 4. Supports 2 kilobytes one-time program ROM, that is abbreviated as OTP. 5. Supports secure boot function for code integrity and authenticity. 6. Supports 32-bit and word-line ReRAM programming function. 7. Supports CRC32 checksum calculation function. 8. Supports ReRAM all-one verification function. 9. Supports ISP and IAP to update embedded ReRAM memory. 10. Supports secure conceal function in APROM or LD-ROM. 11. Supports cache memory to improve ReRAM access performance and reduce power consumption. Next, I will introduce the block diagram. From the left block diagram, it can be seen that RMC is mainly composed of the following 8 components, namely AHB slave interface, bootloader, cache memory controller, 4 kilobytes buffer memory, ReRAM control register, ReRAM initialization controller, ReRAM operation controller, and embedded ReRAM memory. Next, I will share about the memory organization. This memory supports both single bank and dual bank. The embedded ReRAM memory is programmable and includes APROM, LD-ROM, XOM setting page, data ReRAM, the user configuration block, and OTP. The upper right figure shows the address allocation map for each area when using dual banks, while the lower right figure shows the address allocation map for each area when using a single bank. Next, I will introduce the dual bank architecture. The M2L31 ReRAM also provides dual bank architecture where APROM is separated into Bank 0 and Bank 1. For a 256 kilobyte device, Bank 0 address range in the ReRAM is from 0x0 to 0x1FFFF. Bank 1's address range in the ReRAM is from 0x2000 to 0x3FFFF. In such dual bank architecture, a firmware upgrade mechanism is provided, which uses APROM Bank 0 as firmware executing region and APROM Bank 1 as storage region for newer version of firmware. The firmware in Bank 0 can erase Bank 1 and program new firmware to Bank 1 without stopping instruction fetching form Bank 0. The firmware upgrade mechanism here also provides a rollback process to roll back to the original firmware if a new firmware walks abnormally. Such mechanism ensures the firmware to be safe to update in any circumstance. Next, I will introduce the XOM. The execution-only memory, XOM, is used to store instructions for security application, which are not allowed for data access via AHB bus. There are 4 XOM regions in APROM at most. To define a new XOM region, user must complete XOM settings in XOM setting page. For example, to define the XOM region 0, it is necessary to make relevant settings for the 3 registers with addresses 0, XF2, 0, 0, 0, 0, 0, XF2, 0, 0, 0, 0, 4, and 0, XF2, 0, 0, 0, 0, 8. The following principles need to be followed in the XOM application. 1. All XOM regions must be located in APROM with page size alignment. 2. Any XOM region cannot be programmed after its XOM setting is active. 3. Any XOM setting cannot be changed during runtime. 4. The base address of all XOM cannot be set as 0, first page. 5. Only use ReRAM 32-bit program command to program XOM setting page. 6. Clear XOM setting and XOM region by mass erase command or XOM page erase function. 7. User must restart ReRAM initialization to activate any new XOM setting. 8. ICE cannot step in XOM only if debug mode. 9. The valid ISP commands in every active XOM region are chip erase, page erase, checksum, and read CID or DID. 10. The XOM setting page is not accessed, except for chip erase, word program, and 32-bit read. The new XOM setup process is shown in the left figure. The main registers used during the setup process are listed on the right. The XOMR base register is used to set the starting address of the XOM region I. This address must be page aligned. The XOMR size register is used to set the number of pages in the XOM region I, and its minimum value is 1. The XOMR control register is used to control the state of XOM region I. For example, by setting it to a value other than 0x5a and 0x50, XOM region I can be activated. This register will only take effect after a power-on reset. The last 2 registers reflect the current state of the XOM region I. Next, I'll share OTP. The OTP is used to store the important information that are not allowed user to modify them twice. The maximum size of OTP data are 2 kilobytes from 0F310000 to 0F3107FF. Every 64 bits of OTP data has 132 bits, lock bit from 0F310800 to 0F310BFF. Thus, the OTP is 3 kilobytes with location address from 0F31000 to 0F310BFF. The lock bit is for recording if the programmed address had been locked. For example, when lock bit 0 is not 0FFFFFFFF, OTP 0 cannot be programmed again, regardless its content is all 1 or not. The following principles need to be followed in the application. 1. The ReRAM mass erase command are never allowed to be executed in OTP. 2. Before updating the content of OTP from 0F31000 to 0F3107FF, users must check their lock bit firstly. 3. After finishing programming OTP data, users must write a non-zero FFFFFFFF in the lock bit of the above programmed data to make sure that no one can modify them. 4. OTP is only readable by ISP command and unreadable by CPU read directly. Next, I will share the mapping of ReRAM memory, as shown in the left figure. The ReRAM memory map is used for ISP function to read, program, or erase RMC memory. Next, I will introduce the system memory mapping, as shown in the right figure. The address from 0x000000 to 0x000001FF is called system memory vector. The system memory map is used by CPU to fetch code or data from RMC memory. User can write the target remap address to RMC ISP address register and then trigger ISP procedure with the vector remap command 0x2e. In vecmap shows the finial system memory vector mapping address. When chip boots with IAP function is enabled, any executable code, aligned to 512 bytes, is allowed to map to the system memory vector anytime. The system memory mapping supports two startup modes. The one mode is LD-ROM with IAP. By setting CBS, which is the 7th bit of register config 0, to 0, the LD-ROM 0x0F1000000 to 0x0F1001FF is mapping to the system memory vector for Cortex M0 instruction or data access, as shown in the upper right figure. The other mode is APROM with IAP. By setting CBS to 1, the APROM 000000000 to 0000001FF is mapping to the system memory vector for Cortex M0 instruction or data access, as shown in the bottom right figure. Next, I'll share about ISP. ISP function allow the embedded ReRAM memory to be reprogrammed under software control. The ISP provides the following functions: 1. ReRAM clear data buffer function. 2. ReRAM load data buffer function. 3. ReRAM data program function. 4. ReRAM data read function. 5. Company ID read function. 6. Device ID read function. 7. Unique ID read function. 8. Memory CRC 32 checksum calculation function. 9. ReRAM all-one verification function. 10. System memory vector remap function. The specific parameters for each command are shown in the right figure. Note that the target ReRAM memory space that ISP function operates cannot be across banks. ISP procedure example, as shown in the left figure. Steps are as follows. 1. Setting ISP-EN bit field to enable ISP function. 2. Setting the ISP operation parameters, including ISP address, ISP CMD, and ISP DAT. 3. Setting the ISP go bit field to perform the relative ISP function. 4. User can check whether ISP operation is finished or not by the ISP go. 5. The user needs to check the ISP FF bit field to confirm if any errors have occurred. If there is a return value, ISP DAT needs to be read. The following are the notes for ISP operations. 1. After unlocking the protected register bits, user needs to set the RMCI SPCTL control register to decide to update LD-ROM, APROM, or user configuration block, and then set ISP-EN bit field to enable ISP function. 2. The next ISP procedure can be started even ISP FF bit field is kept as 1. Therefore, it is recommended to check the ISP FF and clear it after each ISP operation if it is set to 1. 3. User must wait ISP go bit field to be cleared before asserting chip reset and MCU reset. 4. When the ISP go bit field is set, and then CPU access the same bank, CPU will wait for ISP operation to finish during this period. The peripheral still keeps working as usual. If any interrupt request occurs, CPU will not service it till ISP operation is finished. User can check whether ISP operation is finished or not by the ISP go. 5. When CPU access operation and ISP command are executed in different bank, CPU and ISP command can operate in parallel. Next, I will share the programming of embedded ReRAM memory. First, I will share the 32-bit single-word memory programming, as shown in the figure on the right. Steps are as follows. 1. Clear specific bank data buffer. 2. Load one-word data. 3. Write data. Then, we will show the 32-bit word line memory programming, as shown in the figure on the right. Steps are as follows. 1. Clear specific bank data buffer. 2. Load data buffer. Maximum number of data buffer is 64. Data width of ReRAM is 64 bits. All data will write on one word line, so the address have to be 512 bytes alignment. 3. Write data. Next, I will share the CRC32 checksum calculation. The CRC32 checksum calculation function is beneficial for helping user quickly check the memory content includes APROM, LDROM, and bootloader. The CRC32 polynomial is shown in the right upper figure. The calculation process is depicted in the right bottom figure. Steps are as follows. 1. Perform run memory CRC32 checksum operation. 2. Perform read memory CRC32 checksum operation. 3. Read RMC ISP DAT to get checksum. If the checksum is not 0, the calculation is successful. If it is 0, one of the following situations may exist. 1. Checksum calculation is in progress. 2. Address and size is over device limitation. Both address and size have to be 4 kilobytes alignment. The size should be equal or greater than 4 kilobytes, and the starting address includes APROM, LDROM, and bootloader. Note that the range of CRC32 checksum cannot cross-bank in one operation. Next, I will share the all-one verification. All-one verification function is beneficial for helping user quickly check a memory block content blanking for APROM and LDROM after ReRAM erase operation. The following are the precautions to be followed in the application process. Both address and size have to be 4 kilobytes alignment. The size should be equal or greater than 4 kilobytes. And the starting address includes APROM and LDROM. The range of run all one verification cannot cross-bank in one operation. User can do all one verification in 2 or 3 steps. First, introduce the procedure of the 2 steps. 1. Perform run ReRAM all one verification operation. 2. Read all 1-bit field to get the verification result. If all 1 is 1, it indicates that all the ReRAM bits in the memory block are 1. If all 1 is 0, it means that not all the ReRAM bits in the memory block are 1. Then, introduce the procedure of the tree steps. 1. Perform run ReRAM all one verification operation. 2. Perform read ReRAM all one result operation. 3. Read RMC ISP DAT to get the verification result. If RMC ISP DAT is 0A11FFFF, it indicates that all the ReRAM bits in the memory block are 1. If RMC ISP DAT is 0A110000, it means that not all the ReRAM bits in the memory block are 1. Next, I will introduce the safety protect function in APROM. User needs to write the enable bit at register RMCA-PPROT. Each RMCA-PPROT bit protect 8 kilobytes memory. The RMCA-PPROT 0 protects memory from 0x0 to 0x1115. RMCA-PPROT 1 protects memory from 0x2000 to 0x3315, and so on. Please pay attention to the following notes. 1. When APROM region is protected, user cannot do any programming at protect region, but still can do mass erase. 2. User can also set RMC APW pkeep to lock up the setting of RMC APW prot 0 and 1. When RMC APW pkeep is active, setting of RMC APW prot 0 and 1 can't be modified. When RMC APW pkeep 15 to 0 is 0x55AA, the RMC APW prot 0 and RMC APW pkeep 15 to 0 content cannot be modified. When RMC APW pkeep 31 to 16 is 0x55AA, the RMC APW prot 1 and RMC APW pkeep 31 to 16 content cannot be modified. RMC APW pkeep can reset by all reset source. 3. This function can also be set by user configure. Config 8 is inverse to RMC APW prot 0, and config 9 is inverse to RMC APW prot 1. 4. User should not make APROM function safety protect region overlap with XOM region and secure conceal region. When APROM function safety protect region is overlapped with XOM region, the XOM erase command is forbidden. It consists of 4 protection levels as shown in the figure on the right. They are APWP Level 0, APWP Level 1, APWP Level 2, and APWP Level 3. These levels are achieved by setting the config 10 register to different values. There are 2 points that need to be particularly noted. 1. In APWP Level 0, whether RMC APW Prot 1 or 0 can be changed is determined by RM APWP keep. 2. In APWP Level 2 or 3, whether RMC APW Prot 1 or 0 can be changed is determined by WW pin. If it is low, it is not allowed to be changed. If it is high, it is allowed to be changed. By setting config 10 register, determine which pin WW pin is connected to. If the lower 4 bits of the config 10 register are character A, it indicates that WW pin corresponds to the GPB2 pin. If the lower 4 bits of the config 10 register are character B, it indicates that WW pin corresponds to the GPA6 pin. If the lower 4 bits of the config 10 register are character C, it indicates that WW pin corresponds to the GPC14 pin. If the lower 4 bits of the config 10 register are character D, it indicates that WW pin corresponds to the GPD13 pin. Next, I will introduce the secure conceal function. RMC supports secure conceal function in APROM or LDROM. When APROM or LDROM region is concealed, this region can't be accessed as data or instruction and can't be programmed. The setup steps are as follows. 1. Setting config 4 to describe start address of secure conceal region. 2. Setting config 5 to describe region size. 3. Setting config 6 to enable secure conceal function. These settings will be activated after chip reset. Setting of config 4 or config 5 must be page aligned. Page size in this project is 4 kilobytes. User can set RMCSC-ACT to active secure conceal function. It cannot be disabled by software. Thus, reading SC-ACT will always get one after setting this bit. When using the security conceal function, please pay attention to the following points. 1. The only way to exit active mode after activating secure conceal function is to reset SC-ACT bit field. 2. When secure conceal function is enabled but not active, the secure conceal region should be protect also for ICE path. 3. For ISP path, there is a hardware to monitor ISP command match, config 4, 5 and 6B program and write after secure conceal function is active. If found this action, the ISP will ignore, and this monitor flag is set to 1. 4. After secure conceal is activated, user should set ISP address to 0x0f31100x, where x can be 0, 1, 4, or 8. 5. The ISP command bank remap is not supported when the secure conceal function is active. 6. When arrange secure conceal region, user should not make secure conceal region overlap with XOM region and APROM function safety protect region. When secure conceal region is overlap with XOM region, the XOM erase command is forbidden. Finally, I will introduce the lock effect table. 2 types of security lock protection are supported. The first type is achieved by setting lock to 0 and ensuring that A lock is not equal to 0A5. The second type is achieved by setting KSP lock not to be equal to A5. The lock effect for ICE, ICP, and writer operations is shown in the left figure below. If both security locks are turned off, the areas of APROM, data, LDROM, CFG, OTP, DID, UID, and checksum are all readable. The areas of APROM, data, LDROM, CFG, and OTP are all readable. Once any security lock is turned on, only CFG, DID, UID, and checksum are readable. The lock effect for CPU operations is shown in the right figure below. If both security locks are turned off, the areas of APROM, data, LDROM, CFG, OTP, bootloader, DID, UID, and checksum are all readable. The areas of APROM, data, LDROM, CFG, OTP, bootloader, and secure boot key are all readable. The effect of any one of the security locks being turned on is the same as when all 2 security locks are turned off. It's all for today. Thank you.